Okay, so next up we have a talk by Peter Neri from Aberdeen, which is to do with consistency of classification images across different noise dimensions.
Can you hear me? Start with one. Well, I'm sure your head is already full of noise by now. I'm afraid you can rest assured my talk is not going to do anything to ease your condition. But unfortunately, I have to add more to what you already have. And what I'm going to talk about is the fact that, as you know, there are many different kinds of noise. You've already seen different kinds, the Remy's talk, orientation, pixel noise. This is what I would say is an example of a 2D noise, where each pixel is randomly jittered. And here's perhaps 1D noise predominantly, I mean. So you can see that it varies mostly along this horizontal dimension, not very much along the vertical. This is mainly a distortion of orientation. Of course, there is a lot more in it. And this is an example, perhaps, of a distortion of spatial frequency. This little hand away. So, of course, what we would like is that when we study how the visual system operates, say, in this noise condition, we would like that to tell us how the system operates in other noise types as well. So, we're going to ask two questions. The first one is whether we can apply the same modeling family to each noise type. And when I say modeling family, I don't mean a specific model, but for example, linearity. So it's a tool, if you like. And then I'll move on and ask the question whether we can actually specify a model that will capture all of the behavior across these different noise types. And notice that this specific model need not belong to the same modeling family that may do the job for each individual noise type, as you will see at the end of the talk. So let's move away from those pretty pictures to the ones that we have to use in the lab. Observers had to perform a detection task where the target was a vertical Gabor, as you can see here, the non-target was just blank, and then they added these noise masks. So here's an example of the 2D noise masks, 1D. This is orientation mask, where basically I took a set of oriented Gabors and I just jittered the contrast randomly, and then I added them all to the target and non-target, and the same thing for spatial frequency. There's a set of Gabor where the spatial frequency changed, and then, across this dimension, then I applied construct randomly to all of them and added them on. So let me show you what the stimulus looked like. The probe is in the middle, and as you can see, observers could see any kind of noise within the same block, so it was all mixed. And it was a two-interval choice, so they saw first and second interval there to choose which one contained the target. There were these templates, which are essentially replicas of the signal above and below, because I found that that helped observers focus on what they were looking for within the noise. And primarily because I wanted to prompt observers to adopt a linear strategy like a template matcher, and I found that this paradigm was very good for that. So this is the classification image that you obtain from the 2D noise. For those of you who are not familiar with this, it's the equivalent of the perceptual filter that the observer is applying to the stimulus, the template. And as you would expect, it looks very much like the target, you can see. Now I'm going to average a little bit symmetrically across vertical and horizontal, put some fits so you can see better the structure. This is the 1D classification image, and again, as you can see, it's pretty much what you'd expect. It's essentially a one-dimensional slice through the target. This is the orientation tuning function for orientation noise, and again, it peaks what you'd expect. And this is the spatial frequency tuning function, and again, it peaks where you would expect at the target peak. I was also interested not only whether we could generalize across noise types, but also whether we could generalize across tasks. So I had a subset of the 10 observers I tested. I had them do a discrimination task where they had to discriminate the same target, and now the non-target was a horizontal Gabor, just to check whether we get similar results. And this is what the result for the 2D noise, which as you can see is very similar to the one for detection. This is just confirming that what I'm plotting here is the amount of energy essentially that match the target within classification images for individual observers, each point is an observer, versus the match with the non-target. So you can see that classification images, as you can see here, contain mostly energy that was aligned with the target, but not with the non-target. And this is perhaps surprising because it's unsurprising for detection, because that's what you'd expect from the ideal observer, but for discrimination, the ideal observer predicts that that template should be the difference between the target and the non-target, and it's nothing like that. But it's good news for us because it means that the same mechanism is operating in the discrimination task. Notice that I couldn't do these noise masks because they only modulate horizontally, so they don't really mask the non-target, so I couldn't do the experiments. And I could do the experiment with orientation noise, and as you can see, you get the same orientation tuning function as for detection. And in particular, I want to draw your attention to the fact that this trough here is real. It's in the data, it's not just noise. I'm plotting here the amplitude of the trough, which you can see is negative across the observers, and it's as large, almost as large as modulation in the positive, in the peak. And the reason why I'm pointing out this feature, this particular feature, is that it becomes useful later in the talk. So the conclusion is that the two tasks seem to be supported by the same mechanism. Now we're going to move on and ask the first question: is there a modeling family that we can use to capture all this? And the obvious modeling family to choose is this linear-nonlinear model. For those of you that are not familiar with this model, the reason why I choose is that it's by far the most common, most successful, and a minimal model that you can use in vision. So it's the obvious one to start with. This model makes some very specific predictions that are pretty solid in the literature. One of them is that if you derive this classification image only from noise fields that contain the target, and then you do the same for noise fields that do not contain the target, these two should be the same, and they should look like the linear stage in the linear-nonlinear model. So what you can do is you can apply a test where you just compare these two. If you see any difference, then it means that this model doesn't apply. But if there is no difference, perhaps the model is applicable. If there is a difference, the kind of difference you're looking for is this additional nonlinear distortion that's introduced by a kind of nonlinear machinery that's added on top of this linear stage here. And this term here may or may not show up, depending on the interaction in the equation. I didn't put down the maths because it's kind of boring. But the nonlinear machinery interacts with the signal shape to produce this distortion, but it may not show up if this interaction doesn't work. So a more direct approach is to actually measure this nonlinear machinery and see whether it's there. So if you see what I mean, you may be that there is this machinery and you don't get a difference between these two simply because this term doesn't show up. So I'm also going to try and measure it directly. So what I'm doing here is first I show you that the two images are pretty similar for target present, target absent, which already speaks well for this approach. And then I'm going to plot here for all the observers, nonlinear test 1 and 2, there is nothing. As you can see, it's pretty linear. There is both tests fail to show any substantial nonlinearity. There is no correlation which you would expect for the two tests. And this is the same for 1D noise, orientation noise. You can see target present and absent, red and blue are very similar, and very much for spatial frequency. I'm plotting here an histogram that shows you the distribution for the two tests. It's around 0 across all the conditions. Whereas when you apply some of the metrics to the kind of linear templates that you see up here, you can see there is a lot of structure and it shows up in the test. So the conclusion is that this tool, which is ubiquitous, it's essentially implicitly assumed by most reverse correlation application, is actually applicable. This is good news across all these noise types. Now the next question though is whether we can specify a model that will capture all of this. And what I mean by that is that this model has to be able to take the images, the stimuli, on the monitor, in the screen, and spit out a behavioral response that captures the behavior of the observer. This is very different from just having a general modeling family, which is defined in the dimension of orientation or spatial behavior. This is defined in the monitor, and it's supposed to simulate exactly what the observer is doing. So the most obvious one to start with is a specified LN model, where the linear filter is, say, just a target shape. So this model applies the template of the target to the noise picture to extract the signal. It just does a pixel by pixel weighting and then sums across. And the nonlinear stage is a decisional. Basically, you get the output from interval 1, output from interval 2, from template matching, and you choose the interval that returns the largest number as being the target. How does it do? This model does well for 2D and 1D noise. Don't worry about these small differences. These are irrelevant because they're easy to fix. So you have to do is tweak the parameters of the linear templates. You can get this to aggregate. I'm not interested in that kind of failure. What I'm interested in here is a structural failure of this kind. You can see that the linear model does not capture this negative trough in the orientation tuning function. It it just cannot produce it. So this is a structural failure of this model. You cannot play with the parameters to simulate that. And so it means that now in order to capture everything, we have to move on to a nonlinear model that's outside the LN family, a more complex model. So I'll show you an example of one that doesn't work and then one that works. This one that doesn't work is a push-pull model where you have the vertical and horizontal applied as templates, and compute energy, take the difference. And as you can see, this model does capture the negative trough in the orientation tuning function, as you would expect, because it's got a pull term, but it does not capture the 2D classification image, very poor 1D and not very much of SF. And again, these are structural failures of the model we capture to. So it won't do, even if you tweak the parameters. So the model that does work is the one that you're all familiar with. It's a gain device normalization gain control model where you take the output from these two templates, then compute energy, and use that to divide the output from the one that was the template that was looking for the target. When you run the simple circuit through all these conditions, different tasks and noise types, you can see that it does an excellent job. It essentially captures the whole thing. So let me summarize the results. What I showed you is that the LN family is a useful tool for characterizing the behavior of the observer in relation to each individual noise type that you're using. But if you want to capture the entire behavior across all these different noise types, you have to resort to a different model, in particular, in this case, the gain control model for these tasks and stimuli, that does not belong to the LN family. So at this point, this doesn't seem to make any sense. I mean, if the LN family is doing so well, why shouldn't this be a model that belongs to that family, a specified version of that family? So what I'm going to try and do in the next 2 slides is give you an intuitive, kind of a little bit opaque understanding for why I think this is happening. So I'll start with this silly analogy that you all know about. You've got a nonlinear function, and if it's defined, say, across noise intensity, then if you probe it within restricted regions of this input dimension, it will look linear. So now what I'm going to ask you to do is make a step up in abstraction and imagine that this x-axis is not just noise intensity, but it becomes noise type. So that as you move along this axis, you're basically using different kinds of noise. Your system is nonlinear across this input dimension, but when you probe it locally here, it will look linear. So you can apply LN tools. But if you want to capture the entire behavior of the system across this complex input dimension, you have to resort to a nonlinear model. So that's all, and thank you very much.
Thank you, Peter. We've got a couple of minutes of questions, if anyone has any.
Thanks for the talk. I was wondering the different noise types, were they interleaved in the trials?
Yes. So, sorry, earlier the demo. On each trial, they would get a different noise type and they didn't know which one.
Okay.
So it was all mixed. That's why, so they were doing the same task all the time.
Right. So do you think we would get different results if you were to do
Oh, if you were to block it? Honestly, no, but I don't have the data, but I don't think it will make a big difference. Yeah.
Okay, well, thank you very much.